Why does our universe favor matter over antimatter? Antimatter, the enigmatic counterpart to the familiar particles of our universe, invites us into a cosmic mirror where everything we know is reversed. Imagine a world where the charges of particles are flipped and time itself seems to flow backward. In this realm, antimatter particles, like positrons and antiprotons, dance as perfect opposites to their matter counterparts, maintaining the same mass but with contrasting charges and quantum numbers. Antimatter is not just a theoretical construct. It emerges naturally in cosmic ray collisions and during certain radioactive decays. Though minuscule amounts have been synthesized in particle accelerators, assembling macroscopic quantities remains beyond our current means, confined by the prohibitive costs and immense technical challenges. Yet, the encounter between matter and antimatter is nothing short of spectacular. When a particle meets its antiparticle, they annihilate in a burst of energy, releasing intense gamma rays and neutrinos. This annihilation, a vivid reminder of the universe's balance, is a conversion of mass into pure energy, as elegantly described by Einstein's E1c². As we ponder why our universe is predominantly matter over antimatter, we are drawn to an unsolved mystery: baryogenesis. What cosmic events tip the scales, leaving antimatter as a ghostly reflection of what could have been? Exploring further, we delve into the heart of this cosmic enigma. What does the imbalance reveal about the origins of everything we see? In the cosmic ballet, where matter and antimatter engage in an eternal dance, their presence is more than a shadowy whisper. We glimpse the natural occurrence of antimatter in unexpected places, like cosmic ray collisions high in our atmosphere. Here, antiparticles emerge as cosmic stardust, briefly flickering into existence before annihilating in a burst of energy. Moreover, certain types of radioactive decay offer another glimpse into this realm. Positrons, the antimatter counterparts to electrons, are born in these decay processes, subtly hinting at the universe's fundamental duality. These positrons, though fleeting, become crucial tools in medical imaging, like positron emission tomography. Despite these natural occurrences, antimatter remains largely elusive. Particle accelerators have succeeded only in binding a handful of antiatoms in controlled environments, rendering its creation and containment an extraordinary challenge. The universe, in all its vastness, appears to favor ordinary matter, leaving us pondering the implications of this imbalance. Yet, as we unravel the mysteries of antimatter, we edge closer to understanding cosmic origins. Could the very scarcity of antimatter hold the key to secrets long hidden, whispers of creation echoing through time? As we peer into the cosmic veil, the universe beckons us to uncover more truths, leading us deeper into the mystery of why there is something rather than nothing at all. In a dance as old as time itself, matter and antimatter engage in a cosmic ballet of annihilation. When particle meets antiparticle, their encounter is nothing short of spectacular, a union that results in their mutual destruction, releasing a burst of energy that echoes through the void like fireworks against the backdrop of space. This energy doesn't merely vanish, it transforms, emerging primarily as gamma rays, intense photons that pierce the darkness with their brilliance. But it doesn't stop there. Sometimes neutrinos, elusive, ghostly particles, are born from this cosmic display, slipping silently through the fabric of the cosmos. The energy release is staggering, governed by Einstein's famed equation, E=mc², which tells us that even a minuscule amount of matter can unleash immense energy. It is this principle that fuels the imagination of scientists and dreamers alike, hinting at possibilities both wondrous and terrifying. But amidst the light and energy, a question looms. Why, in our vast universe, does matter outnumber its ethereal counterpart? This imbalance, this cosmic mystery, propels us onward, deeper into the unknown. As we venture forth, we begin to ponder. Could the secrets of creation itself be encoded in the symmetry and asymmetry of matter and antimatter? Yet as we are drawn into the quest to create antimatter, we find ourselves at the forefront of a challenge that is as formidable as it is exhilarating. In the realm of particle physics, antimatter is not merely a concept, but a tangible reality, albeit one that exists in the shadows of its more prevalent counterpart, matter. Within the hallowed halls of particle accelerators, antiparticles are born in fleeting moments, captured only through the most meticulous experimentation. The energy and precision required to bind these antiparticles into antiatoms are immense, resulting in only a few nanograms of antimatter ever being produced artificially. Each particle pairs with its opposite, forming bound states that mirror the atoms of our familiar universe, yet with charges and properties reversed. But here lies the rub. Any attempt to accumulate a macroscopic amount of antimatter is thwarted by its inherent nature. The annihilation of matter and antimatter releases energy according to the mass-energy equivalence, E equals m squared, a potent force that makes containment a formidable challenge. Still, the allure of antimatter extends beyond mere scientific curiosity. What if, in understanding this cosmic mirror, we unlock answers to the universe's very formation? This pursuit is not without purpose, for it whispers of possibilities that transcend our current understanding, luring us into the next chapter, where theory grapples with the origins of existence itself. In a striking paradox, antimatter, often associated with cosmic annihilation, also finds a benevolent role within the halls of modern medicine. At the heart of this transformation is the positron emission tomography, or PET scan. Here, the same annihilative interactions that define antimatter's cosmic dance become a tool for life-saving diagnostics. When a positron encounters an electron within the body, they annihilate each other, releasing gamma rays. These gamma rays are detected and transformed into detailed three-dimensional images, revealing crucial information about metabolic processes and disease states, from tumors to neurological disorders. It is this confounding duality, a force capable of destruction wielded for creation, that underscores the paradoxical nature of antimatter in our universe. In the sterile environments of hospitals, antiparticles help illuminate the mysteries of human health, offering a glimpse into the intricate dance of cells beneath the skin. Each PET scan is a testament to the breathtaking potential harnessed from the universe's most enigmatic materials, charting paths to recovery and understanding. Yet, as we delve deeper into the realm of antimatter, one wonders, could its potential extend beyond the confines of medicine? This question leads us to the next chapter, where we explore antimatter's role in the quest for the universe's hidden origins. As we delve into the enigma of antimatter, we arrive at a perplexing cosmic riddle, the great imbalance of the universe. Modern physics tells us that for every particle of matter, there exists an antiparticle. Yet in the vast expanse of our observable universe, the scales tip overwhelmingly in favor of ordinary matter. Antimatter, though fundamentally the mirror image of matter, is conspicuously rare. So rare, in fact, that its presence seems almost like a cosmic oversight. This puzzling asymmetry, observed in the cosmos, baffles scientists. Theoretically, the Big Bang should have created equal amounts of matter and antimatter. However, the universe we see today is a testament to a mystery that has evaded resolution. Why did matter triumph? The process thought to create this imbalance is known as baryogenesis, an elusive phenomenon that remains one of the greatest unsolved puzzles in physics. If matter and antimatter were produced in such exquisite balance, what force shifted the cosmic equilibrium? Could it be hidden in the depths of the universe's earliest moments? Or is there a clue we have yet to uncover? The journey to decipher this cosmic conundrum leads us deeper into the unknown, where the answers might just reshape our understanding of reality itself. And so, we venture further into the shadows of cosmic mysteries, pondering the unseen forces that have shaped the very fabric of our existence. The early musings on antimatter were more whimsical than scientific, with ideas like negative gravity and anti-worlds filling pages of speculative thought. Yet these notions laid a curious groundwork for future exploration. It wasn't until 1928 that the puzzle began to take a concrete form when Paul Dirac's equations, a marvel of mathematical elegance, hinted at the existence of particles with reverse charges, anti-electrons. Dirac's insights were groundbreaking, but it was J. Robert Oppenheimer's interpretation that illuminated the path towards the positron, a positively charged counterpart to the electron. The enigma of these anti-electrons captured the imagination, culminating in their discovery by Carl D. Anderson in 1932. This was not the end, but merely the beginning. 2 decades later, the revelation of the antiproton and antineutron further expanded our understanding, achieved through the meticulous efforts of researchers at Berkeley's Bevatron. As each antimatter particle was unveiled, the scientific community grappled with profound implications. Could entire celestial bodies, perhaps even galaxies, be composed of antimatter? These questions fueled both scientific inquiry and science fiction narratives, yet they all orbited a central mystery. Why does our universe appear to be missing its antimatter half? In our next chapter, we'll delve into the cosmic scales and hidden symmetries that might finally answer this cosmic riddle. As we venture into the fictional frontier, the presence of antimatter in our cosmic imagination becomes undeniably profound. Antimatter, with its reverse charges and enchanting properties, has fueled the dreams of countless science fiction writers and thinkers, inspiring visions of worlds that challenge our understanding of reality itself. It has been a catalyst for exploring the grandest possibilities, from starships powered by annihilation to entire solar systems composed entirely of antimatter. The concept of antimatter provides a fertile ground for creativity, allowing the human mind to wander beyond the confines of known science. It raises the question, what if there are civilizations out there thriving on the delicate balance of matter and antimatter, living under suns of reversed polarity? Science fiction not only imagines these possibilities, but also invites us to consider the vastness of what could be, expanding our appreciation of the universe's potential. Yet, even within these fictional realms, the reality of antimatter persists as a tantalizing puzzle. Its theoretical potential, coupled with the enigmatic absence of large amounts in our universe, continues to inspire both scientific inquiry and narrative exploration. Could it be that, somewhere amidst the stars, the answers to our deepest cosmic questions are waiting to be discovered?